All right.
All right, awesome. So while he's starting to present, I'll do a quick intro. So Joe Rahmeh has been in design automation for over 30 years. He's participated in design and implementation of tools for noise analysis, timing analysis, place and route, circuit simulation, and test pattern generation. And he's currently at Tenstorrent, and he'll be talking about integrating a high-performance instruction set simulator with FireSim to co-simulate OS boots. So with that, take it away, Joe.
Hi, good morning. My name is Joseph.
Joe, wait, one problem. So it's sharing the PowerPoint design screen instead of the presentation display.
Oh, yeah, sorry. Let me do the presentation slideshow. Is this better?
Yeah. Are you speaking? We can't hear you now.
Okay. So, when you start at Tenstorrent, we do hardware and software for machine learning, artificial intelligence, and we've been working on a high-performance RISC-V processor. And like the previous speaker talked in the keynote speech, we are still kind of stuck in the 90s in terms of the tools and methodologies we use, but we're trying to catch up. Recently, one of my colleagues used FireSim to implement a vector engine for the boom core, and we put that on open source. And then I'll talk today about another project where we used FireSim to help bring up an ISA simulator on an emulation platform. And basically what we're trying to do here, when you start a project, everybody's very excited, everybody's very enthusiastic, and we can do everything. We're going to do it. We're going to finish the project. A few months maybe into the project, reality sets in. And then there is some anxiety. Are we going to be able to finish it? Are we going to be able to finish it on time, on budget? Will it perform? And then, managers start coming around and asking you questions like, can you foretell the future? And you say, no, you can't foretell the future. That will damage your brain. You need to do something different. So I say, okay, forget about the future in general. Can you tell me how this part will behave in the future when it's hopefully become a product? I say, well, we can try, we can simulate. And so that's what we're trying to do, try to simulate, emulate, to try to figure out whether the design is going to work, whether it's going to be performing, etc. So when you're bringing up a design, you start with unit tests, you do bare metal test, and then once the design is mature enough, you want to try something bigger, like booting an OS or running a full application, running spec benchmarks, for example. There's always a lot of interest in figuring out how well the spec benchmarks are going to perform and what kind of score you're going to get. But, running the full spec benchmarks or an OS or a full application is impractical to do on an RTL simulator. It will take a really long time to finish. So the alternative is to use emulation. And FireSim proved a big success for us in terms of allowing us to do emulation at a very low cost and to be able to fire up an emulation environment and do the emulation reasonably quickly. So the idea here is to reduce the bring up debug time. And we want to try to do real-time checking of the emulation results. So you run the OS or an application on the emulation platform, and then you check pretty much cycle per cycle the results of the emulation to see whether or not you're doing the execution correctly. And then you check them against a reference model, in which case it's an ISS simulation that we wrote internally. And then if there is a mismatch, this is again trying to bring up a new design. So you would expect that there will be some mismatches. If there is a mismatch, you stop the emulation at the first mismatch you find. Then you try to generate a snapshot a little bit ahead of the mismatch point. And then you try to run the whole thing again on a RTL simulator, detailed RTL simulator, to try to debug what the problem was. So we use FireSim, we use Chipyard because it provides us a full SoC with all the components you would need to boot an OS or to run an application. And the goal is eventually in the future put our own processor in this platform. For now, we used one of the boom cores, the small boom core, as a vehicle for testing all of this methodology. And then we booted the Fire Marshal Linux image. And we fired all of this on an AWS FPGA. By the way, most of the work that I'm describing here was done by John and Varun. I just did some support for the ISA simulator. So we run the ISS simulator in co-simulation mode and in a client server model where the boom core provides us with a trace of the architectural state, and then we check that trace after each instruction. And we're able to single step the ISS simulator and then to compare the architectural state we get from boom against what we expect from the ISS simulator. And then we're able to change for certain things. For most synchronous events, we expect a perfect match between the emulation on the FPGA and the ISS simulator. But for asynchronous events like a timer interrupt, we would like the emulation platform to set the pace and inform the SS simulator whether or not a timer interrupt should be taken. So this is a system diagram. You have the emulation platform running on the FPGA. It produces a trace of retired instruction. The trace is available to the bridge via DMA. And then the bridge controls the ISA simulator. Basically, it will single step it, just what is the next instruction to be executed. And it will get from it also architectural state. And then it will compare the architectural state we get from the ISA simulator to the architectural state from the FPGA. And then this, in an ideal world, if the model of the RTL is working perfectly, this will match all the way to the end of the boot process or all the way to the end of the application. But in practice, you're going to get some diversions because of bugs in the RTL. And when there is a divergence, we would stop. And then we try to identify what the problem is, try to fix the bug and do this again. So this speeds up the overall bug hunting for bring up in a realistic model where you're trying to run a realistic workload on the simulated system. So again, a recap of the methodology is you'd run the application like the OS boot on the ISS standalone, and we do that because it is fast. And then we make sure that works. Once that works, then we run the app on the FPGA. If it runs all the way through on the FPGA, you're done. There's nothing else to do. But if there is a failure, then we'd run in a cosimulate. If it fails to boot, for example, or it fails, or the application fails to produce the desired results, the expected results, then we run in cosimulation mode, where we're checking after each instruction, the FPGA results against the ISS results. And then we stop on the first divergence. Then we'd run the application on the ISS standalone and produce a snapshot of the memory and the architectural state a little bit ahead of the failure. And then we run the application starting from that snapshot on the FPGA or on the RTL Verilog simulator. and then we try to debug what happened to figure out why there was a divergence, why there is a. And this methodology allows us to kind of zoom in to the fault or to the failure area much quicker than having to do all of this just on the Verilog simulator. Some of the challenges in doing and practicing this is that the cosim would not keep up with the trace coming out of FireSim. And some investigation into this led us to believe that this is because of inter-process communication. So the interaction between the bridge and the ISS was done through sockets. We switched from a socket to an in-memory communication, and that reduced the latency quite a bit. The other part in improving the speed of the check is to check the PC only instead of checking architectural state. And in most cases, that is sufficient. If there is a bug, there is a flaw, eventually the simulation and the emulation will diverge, and you'll see the divergence in a PC change. So if you were just checking for a PC divergence, then that's sufficient. And then we can practice the same methodology of trying to zoom in on the area around the divergence and try to figure out what happened. Another challenge is we currently tried all of this with the boom core, which is written in Chisel. Our own processor is written in System Verilog, and we're not quite sure how this will work, if this will work. We know there is possibility to doing like a black box of System Verilog and FireSim, but we have not practiced that yet. So some of the results, we booted the Linux kernel on both the ISS simulator and on FireSim. It takes about 1.3 billion instructions. We used the small boom configuration, and we ran this on AWS F1. So for runtime comparison, if you boot Linux just on the ISS simulator, it takes about 70 seconds. If you run it on FireSim without cosim, it takes about 130 seconds. If we run it on FireSim with cosim, it takes about 1400 seconds, which is still very practical, extremely practical, much, much faster than you would get if you were to run on a Verilog simulator. So that's all what I got. Any questions?
Awesome. Thanks, Joe. Any questions?
I have a question.
Yeah. Oh, you might want to just come up here.
So when you reach a divergence point on FireSim, how are you, I guess, snapshotting the architectural state back to pass into Whisper, your functional model here? Are you just dumping it out like with printfs at that point, or are you adding extra hardware logic? How are you dumping state from the FPGA sim?
Actually, we currently we're dumping the state from the ISS simulator. We dump all the state from the ISS simulator, and then actually we don't dump the state at the exact point of failure. The methodology we use is to dump the state few hundred cycles before the point of failure. So we would run again just on the ISS and then dump all the memory state and all the register state. And then we can load those register state and memory state into the Verilog simulator and then generate all the waves and then pass it to the RTL designer to see if they can figure out where the bug is, what the cause of the bug, root cause the bug.
So to make sure I understand, you're keeping track of roughly wherever the divergence was at cycle N or something, and then you're basically rerunning or dynamic instruction N. So you have a count of dynamic instructions from the FPGA world, and then you're just getting the same dynamic instructions from the functional model, minus the small divergence, and then you're using that to dump.
Exactly. Yeah.
Perfect. Thank you.
I kind of have a follow-up question to that. Just add a bit on I have a follow-up question to that. Then how do you kind of load this into Validator? Because I think that would be interesting to know.
So into Verilator, we load we have a memory image. We have all the bytes of memory that were modified. So we load these, and then we load the register state by putting a little bit of a bootstrap code that sets the register values and all the CSR values, and then we jump to the PC at which we did the snapshot. So it is relatively straightforward. If you have the full memory image and the register state, you can reconstruct it with a very tiny, like a 100 of instructions of a bootstrap code that will re-establish the register values, and then you jump to the PC at which you did the snapshot.
Okay, and then I have another question, like, do you know how this kind of differentiates or is different from like cosimulation with Dromajo, the other kind of simulator that is available?
I'm not quite sure about that. I don't know much about that simulator, so I'm not able to answer that question.
Thank you. Any other questions? All right, thanks, Joe. We'll move on to the next speaker.
Thank you.